I'm Srikanth Maru, Director of Data Engineering at Cricut. I've spent close to 2 decades building data platforms across telecom, consumer electronics, autonomous systems, and consumer technology. And in the time, I've watched a lot of AI projects launch with enormous ambition. The ones that fail rarely fail for the reason everyone expects. So today, I want to talk about the part of AI that doesn't make the headlines but decides almost everything, the data engineering underneath it. My argument is simple. Most enterprise AI doesn't fail because of the model. It fails because of the foundation. The AI success paradox. Here's the paradox. Organizations are pouring millions into AI, and yet most of these initiatives never deliver measurable business value at scale. And when you look closely, the culprit is never the algorithm. It shows up in four ways. Pilots that look brilliant in a demo but collapse the moment they meet real world volume. Cost overruns, where implementation and maintenance quietly eat the cost of the ROI that was promised on the slide. Delayed deployments, where pipeline bottlenecks push delivery back by months. And poor returns, because the investment went into AI tooling while the data beneath it was left untouched. The common thread is this: the weakness is in the data infrastructure, not in the model. The algorithm is just most visible thing in the room. So it takes the blame for the problems that started much further upstream. Why data engineering is the real foundation? So why does data engineering matter this much? Because no matter how sophisticated your model is, it cannot perform in production on top of unreliable pipelines. Data engineering is the connective tissue that makes AI viable at all. It does three jobs. First, collection and integrations, pulling fragmented sources across the enterprise into something unified. Second, cleansing and feature engineering, turning raw, messy data into model ready inputs. And third, governance at real time delivery, making sure that data is trusted, traceable, and arrives when the model actually needs it. None of this is glamorous. There is no demo moment for a well designed pipeline. But this unglamorous layer is exactly the layer that determines whether your AI survives contact with the real world. Autonomy of AI project failures. When I dissect failed AI projects, the breakdowns are remarkably predictable. And that's actually good news because predictable means preventable. There are 6 recurring root causes: fragmented data sources, poor data quality, hidden technical debt, weak governance, and rigid legacy infrastructure. None of these are exotic. They are engineering problems. We already know how to solve them. But left unaddressed, they create a downstream cascade. Models become unstable, degrading quickly when they are trained on inconsistent data. Predictions get worse, garbage in, garbage out. Except now it's happening at enterprise scale. Costs climb as the maintenance burden compounds, and scalability evaporates because the systems that were never built for production load simply buckle under it. The point I want to land here is these failures aren't bad luck. They are the natural consequence of skipping the foundational work. Hidden technical debt in AI systems. I want to spend a moment on technical debt because in AI systems, it behaves differently than it does in ordinary software, and it's more dangerous. It's invisible until it is catastrophic. It accumulates through shortcuts that feel harmless during development. Feature logic gets duplicated across teams, each with subtle inconsistencies. Manual corrections get baked into pipelines with no documentation. Business rules get hard coded into transformation scripts where governance can't see them. And here's the difference that matters. In traditional software, debt makes your code harder to change. In AI, debt accelerates model drift. It silently degrades the thing your business is relying on, and it raises both your operational risk and your restraining costs, usually without anyone noticing, unless and until a number on a dashboard is suddenly wrong. By then, you're not fixing a shortcut, you're doing an investigation. Let's contrast the two worlds directly. Traditional enterprise systems are engineered for reporting and transaction processing, not for the continuous dynamic demands of AI workloads. Legacy systems are built around batch processing. AI ready systems process real time. Legacy works on static historical data. AI ready runs on continuous learning pipelines. Legacy siloed. AI ready is an integrated ecosystem. Legacy offers limited metadata and it's sufficient. AI ready provides full lineage tracking. Legacy relies on manual governance. AI ready automates policy enforcement, and legacy infrastructure is monolithic, where AI ready is elastic and cloud native. But here's what I would ask to take away from this slide. The distance between these two columns is not a technology gap. You can buy all the technology. It's an architectural philosophy gap. A difference in how you think about data from the very beginning. So let's look into some case studies. The first is manufacturing. The challenge: traditional manufacturing execution systems ran on batch processing. That meant delayed insights, isolated production data, and poor integration across systems, which made predictive AI use cases effectively impossible. The solution was architectural: a multi-agent design coordinating distributed systems, event-driven processing that delivered data at sub-second instead of in overnight batches, and a cyber physical integration that finally bridged the operational technology layer with IT layer, the worlds that historically never talked to each other. The result is the real-time predictive maintenance and process optimization, which translated directly into less unplanned maintenance and improved yield. And notice the win came from re-engineering the data flow, not from the more clever model implementation. Next one is on consumer electronics. So this is a case study on consumer electronics, right? A major consumer electronics enterprise. The challenge here was scale and fragmentation. Data was scattered across completely separate divisions: mobile, home appliances, display, semiconductors, etc. Each with its own ownership and its own definitions, its own systems. Unified customer analytics simply wasn't possible because there was no shared language for what the data even meant. The solution was a unified enterprise data architecture built on a shared semantic layer, an agent-based integration framework that worked across business units and standardized communication protocols that let data finally flow across divisional boundaries. The outcome was holistic customer insight. And just as importantly, cross-functional AI models that had been completely blocked before, not by technology, but by siloed data ownership. Sometimes the hardest barrier isn't technical, it's organizational, expressed as data. The next case study is on autonomous vehicles. The third case study sits at the extreme end of the spectrum. Autonomous vehicles, an area I worked in directly. The challenge is brutal. You are fusing LiDAR, radar, camera, and other sensor data in real time. The requirements are non-negotiable: ultra low latency, high accuracy, and robust calibration. No traditional data platform can meet that. When a vehicle is moving at speed, a pipeline that's usually fast is not good enough. So the answer was a purpose-built perception data platform, engineered from the ground up for low latency inference, capable of handling complex, high-speed environments at production scale. I include this deliberately because it's the clearest proof of my thesis. At this level of demand, you cannot paper over a weak data foundation with a better model. The data engineering is the product. Now, shifting back to the principles, right? Principles of an AI-ready data platform. So if those are the problems of the proof points, what does a strong foundation actually look like? In my experience, it rests on 6 principles. Scalability, elastic compute and storage that grows with your data and your model complexity. Reliability, fault-tolerant pipelines with automated recovery and real SLA guarantees. Flexibility, a modular architecture that adapts as a new data source and your use cases appear because they will. Governance, policy enforcement, access control, and auditability built into the stack rather than bolted as an after the fact. Metadata management, rich lineage and cataloging so your assets are discoverable. And real-time processing, a streaming first design that supports low latency inference and monitoring. The thread running through all 6 is balance, performance, trust, and adaptability held together. Optimize for only one and you have built something that breaks the moment requirements change. Now, let's talk about the 5 dimensions of data quality. Of all those, data quality is the one I've put first because model performance is mathematically bounded by it. You cannot outmodel bad data. That's as simple as that. There are 5 dimensions worth monitoring continuously. Accuracy. Does the data reflect real world values? Completeness. Are critical fields missing? Consistency. Do definitions stay uniform across sources? Timelines. Does data arrive when the model needs it? And reliability. Are the pipelines stable with low error rates? In practice, you enforce this with a few governance habits. Automated validations with the schema and statistical checks right at ingestion, formal data contracts between producers and consumers, quality dashboards tracking freshness and anomalies, and drift detection that alerts you when distributions shift unexpectedly. Do this well, and the payoff is direct. High model accuracy, less frequent retraining, and something harder to measure, but just as valuable is the stakeholders' trust. Metadata and AI governance. If data quality is the fuel, metadata is the nervous system. Without it, teams genuinely cannot explain their decisions, debug their failures, or demonstrate compliance to a regulator. Metadata gives you 4 things: data lineage, end-to-end traceability from source all the way to the model output, explainable AI, which is very powerful, the ability to link a prediction back to the training data, and feature origins behind it. Regulatory readiness, which is audit trails that satisfy GDPR, CCPA, and your own internal risk requirements. And last but not least, experiment tracking, version control of datasets, features, and model artifacts. Here's the practical value. When a model misbehaves in production, and eventually one will, metadata is the difference between a 5-minute diagnosis and a 5-week one. It's the difference between answering, why did the model do that, with evidence or with a shrug. Batch plus streaming, a hybrid architecture. A quick but important architectural point. There's a long running debate about batch versus streaming, and in my view, it's a wrong debate. The answer is both. Batch processing is where you do model training, historical feature computation, regulatory reporting, large scale ETL, etc. Streaming is where you do real time inference, fraud detection, continuous monitoring, online feature updates. A, a hybrid platform lets your AI learn from history and respond to the present at the same time. The reason this matters, most enterprise AI use cases need both. If you architect only for one, you don't just limit yourself, you create blind spots in production that you won't discover until they cost you. AI transformation roadmap. So, how do you get from legacy estate to an AI ready one without betting the company on a single big bang migration? What do? You phase it. Phase one, assess your existing infrastructure and find the real capability gaps across data, tooling, and talent. Phase two, foundation. Improve your data quality, establish data governance standards, define your data contracts. Phase three, modernize. Build scalable pipelines, implement metadata management, adopt hybrid architectures. Phase four, optimize. Automated monitoring, enabling continuous AI operations, and scale across the enterprise. Right? The most important thing on this slide, especially, is which is very easy to miss, is each phrase delivers standard value. You do not have to complete the entire roadmap before you see returns. That's what makes this fundable and what makes it survivable when priorities shift mid-journey, which they always do, right? Now, let me bring together the five key takeaways. One, data engineering comes first. It's the prerequisite for any AI initiative that intends to scale. Two, quality drives performance. Strong data quality governance lifts model accuracy and reliability directly. Three, metadata enables governance. Lineage, explainability, and compliance all depend on it. Four, hybrid architectures win because batch and streaming together cover the full spectrum of real workloads. And five, modernize incrementally. Phased transition lowers your risk while compounding your capability over time. If you take one sentence away from this talk, let it be this. Successful enterprise AI is not built on better algorithms alone. It's built on better data foundations. All right, so that's the Q&A time. So the first question, what are the most common data engineering challenges that prevent organizations from successfully scaling AI initiatives beyond pilot projects? All right. The pattern is almost always the same. A pilot succeeds because someone hand curated a clean slice of data, and then production exposes everything that was hidden. The data is fragmented across silos with no shared definitions. There are no data contracts, so data quality drifts and the schema breaks. Manual fixes and hard coded rules that worked at small scale quietly fall apart. So there's no lineage. So when something goes wrong, nobody can trace it back. And the architecture is batch only, which costs what were never modeled for production volume. So none of these are model problems. They are foundational problems. And that's the reason why many initiatives stall at the proof of concept stage. Okay. So the next question is, how can AI enterprises build modern data architectures and migration strategies that support reliable, cost-effective, and production-ready AI deployments? So to me, the strategy that works is incremental, not a big bang migration. You assess the gaps, fix the foundation, which is comprising of quality, governance, data contracts, and only then modernize the pipelines, and optimize operations. Each phase pays for itself, which is what keeps it funded and survivable when priorities shift. Architecturally, three things matter the most: a hybrid design that handles both batch and streaming, so you don't build blind spots; a cloud native elastic platform with storage and compute decoupled, so cost scales with value instead of exploding; and observability built in from day one: lineage monitoring, drift detection, real SLAs, reliable, cost effective, and and production ready. Like, these aren't separate girls, they're all embedded together. So there's the result of the, same disciplined foundation, I would say. So that's all my time. Thank you so much, for listening into this talk, and appreciate all your support. Thank you so much.